So whatever you know, just write that one. Don't worry about anything. Be careful with yourself. Question number 678, just you need to provide one example. Hello everyone. So Paula's place. I have a lot of funny answers. Some of them I can say without saying the name. Like C60 buckyball has how many hexagon and how many pentagon? Somebody say 0 pentagon. One question is graphene flexible or not? So many of them say no. One question is the prefix nano means, right? So somebody say size of the body. About 0-dimensional, 1-dimensional, 2-dimensional, right? So somebody says it's 2 times same thing like quantum dot, quantum dot. That's not wrong, that's still right, right? Depending on the size. There is one answer about 0-dimensional. So somebody mentioned metals. Only metals, okay? The father of the nanotechnology. So one guy mentioned here, Norio, Danny, I can't read it, it's something like that. one answer about again buckyball, C60 buckyball. So C60 buckyball has 60 atoms, only 60 atoms. So one guy mentioned, I don't know why or that, okay, but someone mentioned C60 buckyball has 205 hexagons and 108 pentagons. It's great, isn't it? Okay, so that's one. Thank you, everybody. So the lecture, this lecture is dedicated for the fundamental, for the very basic about nano and nanotechnology. Very, very basic about nanomaterials and nanotechnology. So here we will cover what is nanotechnology, what is so special about nano, and working at nanoscale, and then some historical things about nanotechnology. Like means before modern era and some major breakthrough in advanced nanotechnology. So these basic things we will cover in this lecture. So how small is nano? So many of you know that one. It's 10 to the power minus 9, 1 billion of a meter. That is 1 nanometer. Definitely you cannot see this with your naked eyes. You need a special tool to go to that one. And if you compare with some other things, so a paper sheet, a standard paper sheet, that is around 100,000 nanometer thick. And then we have like a DNA, that is 2.5 nanometer thick, and human hair can be around 80,000 nanometer in size. And a single gold atom, I'm talking about a single gold atom, that is 1/3 of 1 nanometer. We are talking about here 1 atom. Think about a simple orange, a 0.1 meter in size. If you compare with Earth, Earth is 10 to power 8 times larger than orange. So just imagine what is the relation between one orange and Earth in size. And that is the relation between 1 nanometer and orange. So you can imagine how small it is. 1 nanometer. And the definition of nanotechnology. So definitely means it's understanding the control of matter at the nanoscale. So at nanoscale, what's happening? Either in terms of like properties, in terms of application, in terms of other things that come under umbrella of nanotechnology. So that is called nanotechnology. And at this scale, we have very unique applications, very unique properties, very unusual physical and chemical, even biological properties at that scale can happen. And some of the properties like here, like for example, when we have aluminium, you just decrease the size of aluminium, it will be explosive. Melting point can change, like for example, gold. When you go at nanoscale, the melting point of gold is not that whatever we have at bulk scale. And like some property, new property, for example, antibacterial here for the silver. At nanoscale, that property happens, that property exists, but in bulk, that's not. So at nanoscale, a lot of things can happen, or a lot of new properties can be observed. Some other properties at nanoscale, like material can be stronger, can have unique magnetic properties. And when I say magnetic properties here, one word you are listening all every time when we talk about nanotechnology or computer, that is quantum computing, all right? So quantum computing is happening just due to this nanotechnology. Because at nanoscale, we see that quantum effect where we don't see a standard behavior of the material. And at nanoscale, definitely, we will see like change in the electrical property, chemical reactivity, or that way. For example, change in the color depending on the size. So there are many unique properties at nanoscale that happens. So why is so special about nano? So first thing is scale at which quantum effect dominates. You see here this is a cup that was designed in 4th century. And the beauty of this cup is when you shine light from like either inside or outside, you will see change in the color. Either it's green or either it's pinkish or reddish color. So that color is happening due to some nanomaterial that's at this or that's coated on the cup. And it's still 19th century. And it's in 19th century, it was discovered that this glass, they are impregnated with nano-sized particles of gold and silver, and they are arranged in such a way that when you shine the light, the electrode they reflect in a different way. So that's why we see change in the color for this color. Another example here. If you have a gold and simply decrease the size of gold, so you can see all stay one color depending on the size of gold particles. That's another beauty that's at nanoscale can happen. And again, the reason is here, depending on the size of gold nanoparticle, they interact with light differently. And when they interact with light differently, so you will see different. That's a very unique one and very interesting here. You see, this is a first cube that's 6 centimeters square. No, 1 centimeter square. And total surface area is 6 centimeters square here. Just simply change this cube from 1 centimeter to 1 millimeter. Then the surface area will be 60 centimeters square. But what about if you change it to 1 nanometer? It will be 60 centimeters square surface area. So that's crazy. Surface area can be too much. Like for example, when we talk about graphene, a unique material, 2D material, so very small amount of graphene, even less than 1 gram, can cover a big football field. A very small amount of graphene can completely paint it, can completely cover it. About biology, we, like a human body, we breathe, we take oxygen, and due to oxygen we live, and the reason is for that hemoglobin. So that protein that carry oxygen to the body, and the size of this hemoglobin is 5.5 nanometer. The second key about our body is DNA or RNA. So the size of DNA RNA is also at nanometer scale. Like in this case, for example, DNA is just only 2 nanometer in diameter. So when we talk about nanomaterial or nanotechnology? So two things. How can we see them? How we can fabricate or synthesize them? So to see and manipulate material. So for example, if we are not able to visualize, then we will not find out anything about nanomaterial. Like in this case, for example, this is advanced technology, scanning tunneling microscopy. So using STM, we can find out a single atom on the surface of a film or on the substrate. A single atom. And even we can study the electronic property of that atom. What about manipulating? So these nanomaterials can be manipulated in two different ways. One is bottom up, and the second is top down. So in bottom up, you can start from a single atom, and you can create nano-sized structure. Like for example, you start a simple gold precursor at atomic scale, and you can end up with quantum dots or nanomaterial, etc. The second is top-down. So top-down approach is where you have material at large scale, and simply you break it down till that you don't get at nanometer scale. And the simple technology here, for example, ball milling. Simply you put the bulk material, crush it, and finally you will have very fine powder where particles are at nanoscale. So these are two basic approach to synthesize or manipulate the size of the nanomaterial. And nanotechnology is all around in nature. So if you see around, so you will see nanotechnology all everywhere. The first example here, a gecko. So simply we see a house, right? Sometimes. What is special about this one? It can, like this can walk on the roof or can walk anywhere. The reason is that the unique structure of its feet here. They have it at nanoscale kind of like a very tiny films or pillars like this morphology here, plate-like structure. And when they walk, they can create, like a space of water vacuum there, so they can have a force, addition force between the surface and the wall. And that's what the kind of like idea behind Spider-Man. So simply you have that one, like a particular type of gloves, and you can climb on the wall. And here you see the beauty of this one. Only one toe of this gecko can tolerate an entire body weight from a wall. So that's a very strong force. Another example here, a hydrophobic surface. So if you see the lotus, the leaf, you put any drop, it will not get wet. And that's not about just only this one. There are like a lot of these, for example, butterfly wings. You put a water drop, they will not get wet. And how it happens? What is the specific property they have to repel the water? Again, it's due to nanostructure. So they have some specific type of nanostructural morphology that doesn't allow to interact with water. So that's a high hydrophobicity. This is about like a sea creature. So these, most of them, they don't get any edge on their body. Their body remains clean. And the reason is again their skin that have a specific nano-sized structure that doesn't allow to grow these algae or bacteria. So nanotechnology is all around in nature. And it's not new. It's just really very, very old. So there are some examples from the pre-modern era, and obviously number one is this cup, and again for this cup they have the coating of these nanoparticles, that's gold and silver, and due to those colloidal gold and silver nanoparticles, it has a unique property when we shine the light from inside or from the up. And the reason is that when you shine the light from outside, so it looks opaque but translucent red when light shine through the inside. There is another example that is from 19th to 17th century. So this is a glowing glittering, and again it's unique due to these silver or copper nanoparticle. When we move a little bit forward, so between 6th and 15th century, this is another example, is stained glass window, and especially they use in European building that time they made. And here, again, the unique property or unique feature happen due to these gold nanoparticles. Very unique one. And these nanoparticles, they also work as like a photocatalytic air purifier. So they have the pure air. Another example, when we move towards 18th century, so because that time we have a lot of war, so these swords, they were very unique. They have these kind of like very unique nano structure, like a very, you know, like a very thin sheets, and that's why they were super sharp and strong too. So those were the examples from pre-modern era, but what about modern era? So this is one unique example, 1857, and it's by Michael Faraday, who discovered colloidal ruby gold. And in this discovery, depending on the size of the color, he was able to change the color of the bulk gold. Like another one, 1950. That's a very unique research here. Whoever is working with colloidal chemistry, he or she should know this one. That's a unique one here. So according to Victor Larmar and Robert, they developed the theory, and according to theory, they were able to explain monodisperse colloidal material. And they were able to control the size, not really very in a specific way, but up to one limit, they were able to control the size. So here you see the graph. So in starting, you have the nucleation, and then with the time, the saturation happens. And the size of the particles, like here, for example, is very small, and then it's grow and get bigger. If you are interested about nanoscience and technology, so you should know means who got the Nobel Prize in 2024 in chemistry. Any idea? The fellow who discovered the quantum group, who were able to control the size of quantum. This is the fellow who discovered this chemistry, but the fellow, the scientists, 3 scientists from different countries, who just develop a technology that is called injection technology to control very precisely the size of these quantum groups using this colloidal chemistry. They received the Nobel Prize there. This fellow, Richard Feynman, 1959, that is called father of nanotechnology. And he gave a very interesting lecture. The title, "There is plenty of room at the bottom." So he is called the father of advanced nanotechnology. Gordon Murray, he designed a rule, he developed a rule, and according to his rule, he was telling that every 2 years, the size of the transistor on the chip will double. And it was valid like at least up to 50 years. And here you see very interesting graph here. He had just very few points. Based on these very few points, he was able to conclude or provide a theory that transistor on an integrated chip will double every 12 months, but later it was modified to 2 years. When we are talking about transistor, so how it's moving, how the research is moving here in transistor. So in 2000, the size of the transistor was around 130 to 250 nanometer. By 2014, the size of the transistor was around 40 nanometer. That was developed by Intel. And by 2015, IBM invented a transistor the size 7 nanometer. And 2016, you will not believe, you have a transistor with 1 nanometer size. So you can imagine it on one chip. For example, 1 centimeter by 1 centimeter square chip. How many transistors you can have? And based on number of transistors, you can control, for example, the speed of your laptop, the speed of your any computing device, and a lot of works can happen. These are a couple of scientists. So, yeah, somebody mentioned about this one. No, you know, right? So he called the term nanotechnology, but he is not called the father of the nanotechnology. In 1981, the Bennett and Henrich, they invented scanning tunneling microscopy, and that's allowed to see you individual atom first time on the surface. And they won the Nobel Prize in 1986. So some major breakthrough in nanotechnology. The number one, buckyball, C60. So that is called Buckminster fluorine C60 or buckyball. It has 20 hexagons here and 12 fingers, like a football. And for this research, Carl and Proto and Stanley, they won an award in 1996, Nobel Prize. The second, carbon nanotube. Though credit is given to Izima, who figured it out, carbon nanotube in 1991, the single carbon nanotube. But carbon nanotube was first reported by Russian scientists LV and Gian, and they published a very clear image of multi-wall carbon nanotube in 1952. But somehow, any one of them, they don't have a Nobel Prize for their discovery. In 1993, the MIT scientists say they designed a method to control the synthesis of nanocrystal or quantum dot, and they won the Nobel Prize in 2023 actually. Very interesting line, highlighted the red at the bottom. In 1982, he earned his undergraduate degree from Harvard University, where as a first-year student, he failed his first chemistry exam. And in 2023, he won the Nobel Prize in chemistry. And the method that they developed, that is hot injection synthesis method. In one of the lectures, I will explain that one in detail, how really this hot injection synthesis method works to define the size of your nanoparticles or nanoclusters. In 2004, again, the discovery of graphene and the importance of this material, that within 6 years, they won the Nobel Prize in physics. Within 6 years, that's the fastest. It was just unbelievable. like means how the one fellow can win a Nobel Prize so fast. So when we categorize these materials, so we have 0D, and then we have 1D, 2D, and 3D. So always there is a question, like about 0D and 3D. For example, if I have a 100 nanometer size of the particle, so that will be considered a 0D or 3D. That's the question for you guys. 3D, right? If it is in the range of like 1 nanometer to 10 nanometer, so then it will be 0 levels. But you move forward, then it can be a 3D. Some very unique properties about these 2D materials. I cannot explain all of them, but few of them, they are very, very unique. First, tensile strength. So if you see the tensile strength of these carbon material, and here I'm talking about pure material without any defect. Because if there is a defect, then mechanical property will be weak. So in chemistry, we know like a double bond is very strong bond, right? So in this case, this carbon nanomaterial, like carbon nanotube, they have very, very high mechanical property, and GPA is much higher compared to even steel. So really is strong. And then you have something like that. So some scientists, they just imagine and they become more creative. And that's one imagination. Having one elevator between our two using this carbon nanotube structure. The second, definitely carbon nanotube is very strong, but graphene it's considered the most strongest material yet discovered. They are very flexible. They have transparency, and they are two-dimensional sheet of individual carbon atoms arranged in a hexagonal lattice, similar to honeycomb. You see here a very simple graph. So that graph is a key for many electrochemical reactions, even for some chemical reactions too. So for example here, you have the reactant and then you get the product. So you see here, the energy of the product is less than reactant, right? But to get this product, we need to cross this activation energy barrier. And to cross that activation energy barrier, we need a catalyst there. And those catalysts, if you have a nanomaterial scale or nanoscale, they behave uniquely for that catalyst. Electrical conductivity. So when we have a copper, a question to many physicists who are sitting here: how the electron flow when we use this copper for electrical transport? You met many physicists sitting here, right? Answer, anybody. How does electron flow within copper? That's the question. How the electricity flow through the copper? That's the question.
Vibration.
What is that?
Vibration.
Vibration of. Vibration of what?
So free electrons.
Vibration of?
Free electrons.
Where does those free electrons exist?
So it's the outer shell. In the outer shell.
It's the outer shell, right?
Yes.
And the majority of the electron or the majority of the electron transport happen through the outside or through the center of the copper. Why?
Sir, that's called the skin effect, I think. Sir, the outer electrons only able to connect. The inner cells are due to the nucleus, the gate is not one with it, so they cannot.
You are talking about atomic scale. I'm not talking at atomic scale. I'm talking at bulk scale. When you have a copper wire,
Yes,
how electron transport, how electricity transport through the copper wire. So majority of electron or electricity will flow on the surface or through the wire.
So surface.
On through the surface, am I right?
Yes.
So that's why means when we have these electrical wire cable, so that you will see most of the times they have a bunch of tiny wires.
Multi-core wire.
Yes. And here, same way for the graphene. It's the only 2D material, and you can imagine it has a 3-electron cloud on the top and bottom. So the electron transport for the graphene or the electrical conductivity of the graphene is significantly much higher. Like here, electron mobility is, for example, 200,000 centimeters square per volt second. So it's much higher. Due to surface area or due to unique property of these materials, they can be used for battery application too. Recently, Samsung, they developed one lithium-ion battery based on the graphene, and these batteries, they are 5 times faster and then 60% more battery capacity compared to the standard lithium-ion battery. Simply replacing that material with graphene. In medicine, we are also kind of like moving forward in medicine to use this nanomaterial or nanotechnology. So, like for example, we have these nanoneedle patches. And these nanoneedle patches, if you put on your skin, so it will release very precisely and very effectively drugs there. And like definitely, we have kind of like nanorobots. These nanorobots, they can be used for drug carrier in the human body. And there are some advancements in the field too. Like here, you can see one example. The particle is moving through the this is about targeting or drug delivery, by the way. So in brief, these nanomaterials, they have a very broad application. From healthcare to cosmetic to nanomechanics to automotive industry to etc. So there was one statement like 10,000 years ago, man domesticated plants and animals. Now it is time to domesticate atoms by Professor Susan. So by using these atoms, by playing with the atoms, you can have a unique material. I think that's all for the basic of nanoscience and technology. Any question? So I hope the quiz that you have, at least now you can answer those questions, all right? Go ahead.
So what do you think about Qutub Minar? Just want to know the pillar in the iron pillar in the Delhi.
That's not in Qutub Minar, by the way. There is a separate one kind of like a iron pillar, right?
Yes.
A small. And that doesn't get rusted so far.
That's why I get that. Even my staff asking me about the question I asked. Thanks.
I'm not pretty sure about that one, but that's the unique property of that iron they use there. I'm not pretty sure.
But even still, we cannot make the iron like that.
Yeah, we cannot able to make that. Normally, in the presence of like oxygen, doesn't matter if it comes from the environment or from anywhere. So iron has a property to be oxidized. Yeah. But we don't see that case here. And I think these people have studied that one. Yeah.
Thanks.
There may be many examples in Indian history about nanotechnology. Like Tipu Sultan, right? The weapon, multiple weapons like in ancient days, so they have these nanotechnology stuff.
Sir, actually one thing about this, sir. In like this, you have shown us that why we are emitting sunlight from inside. It shows red color, and if it is light emitting from outside,
Yeah.
it should be color like that. So, is there any particular frequency range in that showing that color, or in visible light itself, is it showing that green and
It's in standard visible light, and the reason is that those particular nanoparticles, they can either transport or emit particular wavelength light, and that's why you see a unique color. Like for example, when you have this gold colloidal solution, right? So depending on the particle size, you shine the simple normal light, but you will see with different color. The reason is that the reflection that's coming with one unique frequency.
because of the vibration, that slide also you have mentioned about some vibrations like that. Slide.
That's an electronic level.
Electronic.
Yeah. How the electron will vibrate in presence of those lights.
Only the vibration energy or any other rotational energy is existing in that molecule.
That will be a combination of both. Any question? So then, floor is open for the discussion. If you don't have any question, what is the next step? Huh? Yeah, one more time. So one more time, you have the quiz in front of you. So try to answer this time.